thank you for showing your video. That feels helpful. So at least we see each other, and that makes it feel like I'm actually teaching to someone, not just to an empty room. Okay, so in last lecture, we talked about seasons and the reason for moon phases. So today we are going to continue on that topic and talk about eclipses. So before I go into that, I want to show a few polls, and so to get the topic started. So let's me launch this poll, and you can answer it on the Zoom call. When we see a full moon in the sky, where is the moon on its orbit? Please give me a quick answer. This is a very simple one, right? It will probably be helpful for me to share this simulation. You can see if the sunlight is coming from here, where on the orbit will the moon be in the full moon position? Most of you have answered it, and the majority of you got it correct. The correct answer is the first one. It's on the opposite side of the orbit from the direction of the sun. So if the sunlight is coming from here, you will see a full moon when the sun is over here, right? So when the sunlight is coming from here, the side of the moon that is facing the sun is going to be bright. And if it's on at this position, from the Earth's perspective, we can see the 100% of the illuminated side, 100% of the bright side. So it will look like a full moon. If it was on the other side, if it was on the side towards the sun, then on Earth, what you can see is the dark side of the moon, so that you don't see any reflection of sunlight by the moon. So this is the new moon position. This is the full moon position. So it has to be on the side away from the sun, opposite side of the orbit from the direction of the sun. Now let me start the next one. When the moon passes through Earth's shadow, what do we see? Where on the orbit will it be? Did I end the poll? Sorry about that. How do I, let me share the poll again. Sorry about that. Sorry, I didn't see, how do I relaunch poll? Okay, relaunch. You may have to please click again. I accidentally ended the poll. When the moon passes through Earth's shadow, what do we see? Okay, most of you have got it correct. When the moon passes through Earth's shadow, we see a lunar eclipse, right? And that is when the moon is in the Earth's shadow, sunlight cannot reach the surface of the moon, so it cannot get reflected by the moon. So what we see is that we don't see any reflection from the moon, so the moon appears to disappear. So the moon basically disappears from the sky almost. And in that case, we think the moon is being we say the moon is being eclipsed, or basically it disappears into the dark sky, and that is what we call a lunar eclipse. And where can it happen? It can only happen when the moon passes through Earth's shadow. Where is the Earth's shadow? Earth's shadow is on this side, right? Is exactly the same place as the full moon position. So when the moon is on the opposite side from the sun, on the opposite side of the orbit, away from the sun is over here, the moon is over there. When the moon is here, we will usually see a full moon, but this is also the place when it can get into our shadows. So now, do you see a problem? Should we be seeing a lunar eclipse every month? Now let me launch the third poll. Yeah, lunar eclipse happens when it is in Earth's shadow, and the full moon would also happen when it is at this position on its orbit. Should we be seeing a lunar eclipse every month? Do we get to see that every month? Now think about it. So the majority of you answered this question correct. The correct answer is indeed it can only happen around full moon, but not every month. We don't get to see a lunar eclipse every month. We only hear about lunar eclipse or see lunar eclipse once in a while, right? It's maybe at most once or twice a year, and that is kind of a rare event. We don't see a lunar eclipse every month. But why? Why we don't see a lunar eclipse every month? I mean, shouldn't the moon be in the Earth's shadow when it is at the full moon position? Why don't we see a lunar eclipse every month? Anyone want to answer this question? Just sharing the result of your poll with you, so that most of you got it correct. It can only happen around full moon, but not every month. You can type your answer into the chat and to everyone, or you can also unmute yourself and speak up. Why don't we see the moon every month? See the lunar eclipse every month? Any guess? Anyone? No one? No one knows why we don't see lunar eclipse every month? Okay. And now collinear every month. That's a good answer. Yeah, great. Adia also said because the moon's orbit is tilted. So thank you, Li Lap Yan and Adia. So now let me start my lecture slides so that you can see this. Let me put the lecture slide first onto the first slide. Wait, can you see? What do you see?
Yeah.
Okay, sorry about that. Now I'm sharing my whole desktop, so that makes it easier. When we see a lunar eclipse, we don't see it every month. We only see it occasionally, certainly not every month. But the only time we can see it is when the moon is in the Earth's shadow, so it has to be in the opposite side of the orbit, away from the sun. And that is the position of the full moon. So today's lecture is about eclipses, and we are going to talk about lunar eclipses and solar eclipses. So lunar eclipse is when the moon passes through Earth's shadow. So when the moon passes through Earth's shadow, this is a sequence of pictures showing the process of a lunar eclipse, initially you see a full moon, and then the full moon enters the shadow of the Earth. And you can see here, this half of the moon is already in the shadow, and this half of the moon is not in the shadow yet. And then in the next picture, so first of all, this picture is a composite picture. So this is the photographer has taken many pictures and then put all these pictures together to form a string of moons to show you the whole sequence. So initially it was partially covered, partially not covered, it's partially in the shadow, and then the shadow covers more and more of the moon until the whole moon is in the shadow. When the whole moon is in the shadow, it gets really, really dark. It doesn't completely disappear from the sky. You can still see the moon in the sky. It kind of look kind of reddish or yellowish, and I'll tell you why. But it is much, much darker than what a full moon would look like. So this is the process of a lunar eclipse, that is when the moon gets into the shadow of the Earth. So that's lunar eclipse. And what is a solar eclipse? Solar eclipse is when the Earth passes through the moon's shadow. So when the moon is in between the sun and the Earth, we can get into the shadow of the moon. So if we happen to be at the spot on Earth that is in the shadow of the moon, the sun will be blocked by the moon. So here, this is the disk of the sun that is being blocked by the disk of the moon. And you can see it is completely dark in the middle because this is the dark side of the moon, and you cannot see any reflection of sunlight from it. So it looks completely dark, and the sun, the bright disk of the sun is behind. And you see these feather-like stuff around the sun, and these are the corona of the sun. This is the upper atmosphere of the sun. It is actually much, much dimmer than the disk of the sun. So usually when the solar disk, the round disk of the sun is not blocked, we will not be able to see the corona. But when the disk of the sun is blocked by the moon, you can start seeing things, these fainter upper atmosphere of the sun in the dark sky. So that is visible. And so solar eclipse is when the Earth passes through the moon's shadow, so the moon is blocking the sun. So these are the two kinds of eclipses. Why doesn't eclipse happen every month during full moon? So that's the reason, as I has already said, is because that the disk, the orbital plane of the moon, is tilted relative to the orbital plane of the Earth around the sun. So here this yellow disk in the middle is representing the sun, and this bluish disk is representing the Earth. The Earth goes around the sun in a nearly circular orbit, and this picture is showing it from the side. So we're looking at the orbit from the side. And then the moon is also going around the Earth in a nearly circular orbit, but a much smaller orbit, of course. And here, this little circle represents the moon, and the moon is going around the Earth. So when the Earth is on this position on its orbit, and the moon is on the opposite side away from the sun. So sun is over on the left side of the Earth, the moon is on the right side of the Earth. We will be able to see a full moon, right? So this left half of the moon will be illuminated by the sun, so we can see the full bright side of the moon, so we see a full moon. But it's not going to show you an eclipse because sunlight can still reach the moon, and it's not going to be blocked by the Earth. The Earth's shadow will be over here in the line that is connecting the sun and the Earth. And if you extend that line over here, this is the shadow of the Earth. The moon is not in the shadow because this orbital plane is tilted. Because this alignment is not perfect, so that if the Earth is at this position, we don't see the moon being eclipsed. Similarly, on this other side, the moon will also not be eclipsed because the sunlight can still reach it. The moon is not going to be in Earth's shadow. However, when the Earth is over here, at this position, one that the moon is on the opposite side of the orbit, of Earth away from the sun, it will be going into the shadow of the Earth. And so in this place on the orbit, when the Earth is at this place, and when the moon is on the opposite side of the orbit from the sun, then we can see a lunar eclipse. And that is going to happen around full moon time. So this is when these perfect alignment can happen. At these other positions, these perfect alignment cannot happen. So that is why we do not see a lunar eclipse every month. Here is another picture trying to explain this. So you can imagine that we can put this, the orbital plane of the Earth around the sun on a water surface. So imagine there's a pond. This is that you have a water surface, this blue water surface, and let's put the Earth's orbital plane on this water surface. And then because the moon's orbit around the Earth is tilted, so sometimes the moon goes above the water, sometimes it goes below the water, right? And when we will see a full moon is when the moon is on the opposite side of the orbit away from the sun. So for example, in this position, this is a full moon position. When the Earth is over here, this is the full moon position. It has to be on the opposite side away from the sun. And at this position, this is the full moon position, or on the in this position, this will be the full moon position. So it's always on the far side when it says away from the sun, you see a full moon. But in not all of these cases, you will see a lunar eclipse. For example, here you can see the shadow of the Earth. In this place on the orbit, the moon will actually be below that water surface, below the Earth's orbital plane. So it will not be going into the shadow. Here it is above the water surface, it's not in the shadow, but in these two places, it will be right on the water surface, so it can be in the shadow of the Earth. And so in these 2 months, we will be able to see lunar eclipse. So lunar eclipse actually happen only in particular months of a year, and it doesn't happen in every month of a year. So now let's check out another animation in the class action app, as I showed you before. Actually sharing my screen is not a bad idea. Let me still share my full screen. So we have this class action app, and then there's a moon inclination simulation. You can see this is animation that is showing the thing to their true scale. So if you are looking at the Earth and the moon from the position of the sun, so suppose we are on the sun and we're looking toward the Earth. So the Earth is a little circle on its orbit. This green line is the orbital plane of the Earth. And this little green line is the orbital plane of the moon. And you can see a little dot is moving around on its orbit. And this is how small they are in space as viewed from the sun. So they're tiny, tiny dots because the distance between these objects are really, really far compared to their sizes, as we talked about before, right? You can see that as viewed from the position of the sun, this orbit keeps changing. The tilt of the orbit keeps changing, but it's not really changing that fast in space. But because the Earth is going around the sun, sometimes the moon's orbital plane is tilted toward the sun, sometimes it's tilted away from the sun, sometimes you can see it from almost a completely edge-on perspective, or completely from the side of the orbit. So this is why it's very difficult to form a perfect alignment between the moon, the Earth, and the sun. And so you can see over here, this is a zoom in window showing the moon passing by the Earth. So this is a window looking at the region around the Earth, and we actually just had an eclipse. So you can see if I drag it backwards and slow it down a little, you will notice that the moon passing by, right? Let's show that again. You will see the moon passing by. Slow it down further. And you can see now it is passing by. It is very quick. And now if I try to, may need to slow it down even further. So now 1 second represents 1 day, and you see the moon is passing by and actually went into the Earth's shadow. Actually, it seems to be in front. Now, after it come back, we will see it go behind the Earth, and that is when it is in the shadow of the Earth. Okay, do you see that? So this is when you can have perfect alignment. So you see it going behind the Earth. But at other times, you don't see a perfect alignment, so you won't see a lunar eclipse in those months. And you can see that every year there's about 2 months in a year that can have eclipse, and that's roughly separated by 6 months. And this cycle is not perfect, the same as a year, because you don't have an integer number of months every year. And so the eclipse seasons every year will be slightly different, but they're always only about 2 months in a year that can have eclipse. Now let's go back to the slide. Any questions about this? I don't see any. Okay, that's good. No questions. So when will we see the next lunar eclipse visible in Hong Kong? There will be a lunar eclipse in November of this year, and it's going to be a total lunar eclipse. One lunar eclipse happens, you see this everywhere on Earth because the moon is in the shadow of the Earth. So basically, the whole side of the bright side of the moon is in the shadow, so it doesn't receive sunlight. Everywhere on Earth can see this phenomenon as long as you are on the night side. As you are on the side that is facing the full moon, you will be able to see it. And so you can. This is not that rare an event. Almost every year you will have a lunar eclipse. Sometimes it's a total lunar eclipse. Sometimes it's a partial lunar eclipse. So now let's answer this question. When will we see a solar eclipse? Do we see it every month around new moon, or every month around full moon? Or it can only happen around new moon, but not every month, or only happen around full moon, but not every month? Let me start this poll. Still sharing the result. I hope when I have the poll result shared, it doesn't block your view of the slide. Okay, most of you have answered, so I end it now and share the result. So the correct answer is the one that is chosen by most of you, and it can only happen around new moon, but not every month. So that's the correct answer. And the reason is that the moon has to be in between the Earth and the sun for the moon to cast a shadow on Earth, so that the moon can block the sun. When we call it a solar eclipse, it is the sun that is being eclipsed. But what we mean by eclipse is means that the sun disappears in the sky, right? And so it has to be blocked by the moon, so that the moon has to be in between the Earth and the sun. And at this, it can only happen at this new moon position on its orbit. So it can only happen around the new moon time, but not every month, because the perfect alignment doesn't happen every month. Okay, so that is the frequency of eclipses. It only happens in roughly 2 months every year. Now let's talk about different kinds of eclipse and some details about eclipse. So the lunar eclipse is when the Earth lies directly between the sun and the moon and casts its shadow on the moon. And you should notice that the lunar eclipse actually looks quite different from the phases of the moon. So we know that now that the phases of the moon is not caused by the shadow of the Earth. The phases of the moon is formed because that when the moon is at different positions on its orbit, we see different fraction of the bright side of the moon. Because the bright side is always facing the sun, but that bright side sometimes is facing away from us, so we don't see that. And depending on how much of the bright side we see, we can see different phases. Sometimes it's a crescent moon, sometimes it's a gibbous moon. And that is very different from an eclipsed moon. An eclipsed moon is when it is in the shadow. And you can see that when it is in the shadow, these curvatures are indeed telling us about the shape of the Earth. Because the Earth is round, our shadow is also round, right? So these, when you take a picture of a lunar eclipse, you can see this line that is dividing the darker side and the bright side is indeed that part of a shadow, a part of a circle. So the Earth's shadow is much bigger than the moon because our Earth is bigger than the moon, and its shadow, even though it is casted away from the moon, it's still away from the Earth, is still bigger than the moon. And so you can see this curvature that you are seeing in these pictures. These are indeed part of a big circle that is telling you the shape of the Earth. And so in the ancient times, people can tell, or intelligent people can tell that the Earth is actually round just by looking at eclipses. So I think that some intelligent people in the ancient times knew that the Earth is round even before Magellan circled around the Earth. They can tell from the shadow of the Earth cast on the moon because its curvature is round. You can see that. And you can see that is very different from the gibbous moon. A gibbous moon, you can see that this, when we can see more than half of the bright side, this dividing line is a convex figure. So that means that it's bulging out. The bright side is bulging out. So it is a convex curve. But in here, in the eclipse, this is a concave curve. So that is very different. So this is, just notice this big difference. And then let's talk about different types of eclipses. To understand that, I have to tell about two parts of a shadow. Because the sun is not a single point, the sun actually has an apparent size in the sky. If you look at the sun, there is a big round disk, and that disk is about 0.5 degrees in the sky. And because it has a size, our shadows, it doesn't have a sharp boundary. So if, for example, if you studied your shadows on the ground, you will see the boundary is not that sharp. The reason is because the sun is an extended object. It's not a point source, it's a big disk. And actually, in reality, it's much bigger than the Earth. So when the sun is casting a shadow for the Earth, the shadow actually has two parts. There is a part called the umbra part. This is the darkest part of the shadow. Within this part, none of the sunlight can reach it. And this is the darkest part of the shadow. But there is also a part of the shadow that is only partially shadowed, and this is called the penumbra of the shadow. The shadow has two parts, umbra and penumbra. In this part, some sunlight can still reach that region, but some sunlight cannot reach there. For example, we can show you that from this top, in this figure, the top part of the sun is able to reach this point in the shadow, right? Because a straight line, if I draw a straight line, they can reach there. And this part is just barely able to reach there, but the bottom half of the sun is not able to reach that point in the shadow. So if you're looking toward the sun in here, you can only see half of the sun, not the complete sun. So basically, this is partly in the shadow, but not completely in the shadow. So it is, this region is not going to be as bright as the part outside the shadow, but it's also not going to be as dark as the umbra part of the shadow. So we call this the penumbra part of the shadow. So that is when you can have 3 different kinds of lunar eclipse. So when would you have a total lunar eclipse is when the moon is completely in the umbra part of the shadow. So when the moon is completely in the darkest part of the shadow, you can see from here, you cannot, none of the light from the sun can reach this point. So this is when we have a total lunar eclipse. But if the moon is only partially is passing through only part of the umbra and part of the moon is still in the penumbra part, then this part that is in the penumbra part can still receive some sunlight. And it can receive, say, some more percentage of sunlight. So that is this part. That is the part that is still bright because the sunlight is very strong. Even if you see half of the sun or like 10% of the sun, it is still going to give you a lot of light. And so this is when we will have a partial lunar eclipse. That is the part of the sun, part of the moon is in the umbra part of the shadow, and part of the moon is in the penumbra part of the shadow. And when it is in the penumbra part, this is not going to be as bright as a full moon usually. So if the moon is, if a full moon happens over here, it can be much brighter than this part of the moon. So even during a partial lunar eclipse, even the bright half is not going to be as bright as usual because it is only seeing part of the sunlight. And that is also why that this edge of the shadow looks kind of fuzzy, because that closer to the edge, those places on the moon are receiving less and less sunlight. They may only see a few percent of sunlight, so they become much darker than the part that is far away from the umbra penumbra divider. Okay, and also there is a third kind of eclipse that is usually not talked about a lot in the media, and this is called the penumbral eclipse. This is when the moon misses the umbra completely, but only going through the penumbra part of the shadow. If the moon, the alignment happened to be that the moon, when it is going through the full moon position on its orbit, is only going through the penumbra part, then the moon will get a little darker than usual. The full moon will get a little darker than usual, but you will not notice a very obvious disappearing of the moon, so that you will not see half of the moon disappear. It's just going to get a little darker, and that's all. It doesn't. It's not a very easily noticeable phenomena. So that is why this eclipse, this kind of lunar eclipse, is not talked about a lot. But it's called the penumbral eclipse because the moon is only going through the penumbra part of the shadow. Okay, so that's 3 kinds of eclipse: total lunar eclipse, partial lunar eclipse, and penumbral lunar eclipse. Now, the next question I want to answer is, why is the moon red in total lunar eclipse? So here is again another sequence of images. And you can see in this picture over here that this is, again, this is many pictures taken separately, but then put together into a single picture. This shows you how it is, how the lunar eclipse is proceeding with time. This is the beginning part of the lunar eclipse. The moon is being eclipsed for a small fraction, and then a larger fraction disappearing to the shadow. And most of the moon is disappearing into the shadow. And then when the moon is completely disappearing into the shadow, you can still actually see it. How can some light can still reach it? You may think why this actually looks brighter than that one. Why is that? The reason is that these different pictures, they are taken with different exposure times. When the moon is only partially in the shadow, the moon is actually very, very bright. So the photographer took this picture with very short exposure time so that the moon is not overexposed. But when the moon is completely in the shadow, it's actually gets a lot darker than that. In reality, this one is a lot darker than that one. But the photographer took a longer exposure time, so it overexposed it so that you can still see the moon. And so that it's not that when it is completely in the shadow, it's going to be brighter. It's not. It's going to be darker than these other situations. It's just that the exposure time is longer. But why can we still see it? Why can some light still reach it? Is the moon giving off light by itself? No, it's not giving off light by itself. The reason is because our Earth has an atmosphere, and the atmosphere can refract sunlight. The sunlight is basically completely blocked by the Earth when the moon is in our shadow, that most of the sunlight cannot reach the moon directly. But because our Earth has an atmosphere, a very, very thin atmosphere, but that atmosphere can refract the light, can redirect the light towards the moon. And so that is why there's still some light that is being reflected by the moon. And the reason it is red is because our atmosphere is very efficient at scattering blue light, but not very efficient at scattering red light. So most of the blue light gets scattered in the atmosphere so that they get scattered and absorbed in the atmosphere. But the red light can pass through the atmosphere more efficiently. So when it gets refracted, most of the light that is left behind are red light. And so that is why the lunar eclipse looks red. And if you're on the moon at that time and looking back towards the sun, this is the picture you're going to see, that you basically, if you have an astronaut standing on the moon during a lunar eclipse, the astronaut is going to be seeing a solar eclipse, right? If you are looking from the position of the moon, the Earth is blocking the sun. And what the astronaut is going to see is that although the Earth is blocking the sun, you can actually see a reddish atmosphere. And that is the red light is aiming towards the moon. That can be seen by the astronaut standing on the moon. And this is the same reason that why the Earth's sky is blue. Why do we have a blue sky? Because the atmosphere of our Earth is very efficient at scattering blue light, so that during the day, all the blue light gets scattered around so that we have a blue sky. And this is also the same reason why when a sunset looks red, the sun looks red during a sunset or sunrise, because during sunrise or sunset, the sun's light has to go through a much larger thickness of the atmosphere. So there's a lot of scattering of blue light. So blue light gets scattered away, and the only thing that is remaining is red light. So that is why sunset always looks red. And so this is also why the total lunar eclipse, the moon will look red. Okay. So here is a picture of that, and you can still see it. You can still recognize features on the moon, but it is a reddish moon. So that is a very beautiful picture usually. So that's why the photographers always give it a longer exposure time to get sufficient light. Okay, any questions about that? Okay, good, thank you. What time is it? 3:10. Okay, let's talk about solar eclipse. So solar eclipse is happening when the Earth is in the shadow of the moon. But because the shadow of the moon is much smaller compared to Earth, the shadow of the moon is even smaller. And because also we are at a distance away from the moon, we only usually have a tiny portion of the moon's shadow on Earth. So when we have a solar eclipse, not everywhere on Earth can see this, and it only casts a tiny shadow. Only a tiny region of the Earth can see the sun being blocked by the moon. So the solar eclipses are relatively rare for a particular place on Earth, and it actually doesn't happen that often for every location. And also we can have total or partial solar eclipse. Again, that is related with the two parts of the shadow, the umbra part of the shadow and the penumbra part of the shadow. So here you can see this is sun, the moon, and it's casting a tiny shadow on the surface of the earth. And the shadow usually is only a few tens of kilometers or at most a couple hundred kilometers wide. But the Earth's radius is 6,400 kilometers, so it is much bigger. So for most part of on Earth, you cannot see the total solar eclipse. Only tiny region on it can see, but the other part that is around that region will be in the penumbra part of the shadow. And what will happen to this region? Remember that in the penumbra part of the shadow, only part of the sunlight can reach it, and part of the sunlight will get blocked by the sun, right? And so in these places, people on Earth will see a partial solar eclipse because the sun will be partly blocked by the moon. And so that these regions will see partial solar eclipse, but in the umbra part of the shadow, those people will see a total solar eclipse. Again, it's because only part of the sunlight can reach those locations. And so that those regions will see a partial solar eclipse. And partial solar eclipse looks like this, that the sun becomes a crescent because the moon is blocking part of it. Okay, so it is that when you see this on the sky, you're in the penumbra part of the shadow. You are seeing only half of the sun. And if you have a total solar eclipse, you're lucky enough that you're standing right in the tiny part of the umbra part of the shadow, then you will see the sun getting completely blocked. The disk of the sun will get completely blocked, but then you can start seeing, when the sun gets blocked, the sky gets really, really dark, because the sunlight is the light source for us during the day, right? And when the sun is blocked, the whole region in that shadow is going to get very, very dark. And the sky will also become dark, and you can even see stars during the day. And then you can start seeing the atmosphere of the sun that is now comparably bright compared to the dark sky. And so this is the corona of the sun. So that this is always, that's why the solar eclipse pictures always look like there's a feather-like features around the sun, these fuzzy feather-like features around the sun. This is the upper atmosphere of the sun. And then there is actually another possibility for solar eclipse. There's a third kind of solar eclipse called annular solar eclipse. And how can that happen? The reason is because the moon, the orbit of the moon around the Earth is not a perfect circle. The moon around the Earth, the moon's orbit around the Earth is a slight elliptical orbit. And so that means sometimes the moon is a little closer to us and it look bigger on the sky. Sometimes it's a little further away from us and it look smaller on the sky. And so that's why we sometimes in the newspapers, you can see supermoons, or that is because when you have a full moon, it also happens to be close to Earth. And then that is the time when you say we have a supermoon, because it looks bigger than usual. And when it is big, when it is closer to the Earth, the angular size of the moon will look a little bigger than the angular size of the sun. And so we can get into the umbra part of the shadow to see a total solar eclipse. But when the moon is slightly further away from the Earth's orbit, the moon will look a little smaller in angular size compared to the angular size of the sun. And in this case, the shadow of the moon doesn't even reach the Earth. The umbra part of the shadow that cannot reach the Earth. So only the penumbra part of the shadow can reach the Earth. And so you can, in these places, you can see a partial solar eclipse. But what happened to the right in the middle of this penumbra ring? Is that at those places, the center part of the solar disk, the light cannot reach this location on the ground, right? But the edges, the sunlight from the edges of the sun can still reach it. And so this is when you will have an annular solar eclipse. In this picture, this black circle is representing the moon. This is actually the moon itself. It is basically blocking the disk of the sun, but it's not big enough to block the whole sun, and it's can only block the central part of the sun. So you can see that the sun is making a ring around the moon. So this is basically, you can still see the edges of the sun, but not the center part of the sun. This is because if you are lucky enough, you happen to be at this position, you can see an annular solar eclipse. So that's why we call it annular, because it forms an annular ring. Okay, and this can only happen if the moon is happen to be slightly further away from the Earth, so it looks a little smaller than the sun. And we are actually very lucky on Earth that we are very lucky to be able to see all three kinds of solar eclipses on Earth. And that is due to a complete coincidence that the sun and the moon, their angular size in the sky, or their angular extent in the sky, is both about 0.5 degrees. How large is 0.5 degrees? If you hold out your arm, you now look at my video camera, you hold out your arm and look at the fingernail on your thumb, okay, on your thumb, and that the width of your fingernail is at an arm's length is about 0.5 degrees, and that is 0.5 degrees in the sky. And now you can go out and look at the full moon and then compare it to your fingernail at arm's length. That is about 0.5 degree. You can see it's about the same size as the moon in the sky. That is same angular size. And then both the sun and the moon are about the same size. Just happen to be a coincidence because the distance between the sun and the Earth and the distance between the moon and the Earth and their sizes just happen to be that they're both about 0.5 degrees. So which kind of solar eclipse we can see depends on how far away at that moment the distance between the moon and the Earth. If the moon is happen to be on its on the far side of its orbit, so it happen to be slightly further away from the Earth, then we see an annular solar eclipse. But if it happen to be just closer to the Earth on its orbit, then we'll see a total solar eclipse. And suppose that if we make the moon's orbit 10% closer, if we just reduce the lunar orbit by 10%, and then we will never see an annular solar eclipse because the moon will always look bigger than the sun. And so whenever it blocks it completely. On the other hand, if the moon were just 5% farther away from the Earth, let's make the lunar orbit 5% bigger, then we will never be able to see a total solar eclipse. And so we're actually just very, very lucky, and that the current position of the moon's orbit is just happen to be at the right distance, so we can see all three kinds of solar eclipses. And as a matter of fact, the moon is actually gradually moving away from the Earth because of tidal forces. And because the moon's orbit is not a perfect circle, and remember that I told you last time that the moon's rotation around its own axis and its orbital motion around the Earth is perfectly synced up, and that is due to the tidal force of the Earth acting on the moon. And because it's on an elliptical orbit, so that synchronization is not perfect, but the tidal force is trying to make it into a perfect match. And as a result, that is keep pushing the moon away. The moon is actually getting slightly further away from the Earth every year. But that speed is very small. So there's maybe a few centimeters a year it gets further away from the moon, from the Earth. So in thousands of years, after thousands of years, or millions of years, I don't really know the number. in my head. But after a long time, the moon will get far away enough, and then at that time, for people on Earth, they will never be able to see a total solar eclipse again. So we are just living in the right time in history, so we can see all three kinds of solar eclipses on Earth. And as I said, that the total solar eclipse is a very rare event for a particular location on Earth because the shadow covers only a tiny portion. And for any given single location on Earth, a total solar eclipse occurs only once every 300 years also. And so it's a long time. And here is a picture of the moon's shadow on Earth as viewed from the International Space Station. So you can see Earth is much bigger than this shadow. This shadow is only about 100 kilometers in size. And so but in that region, it is very, very dark because it's not shine, none of the sunlight can reach it. So I wonder if anyone of you have ever seen a solar eclipse before, a total solar eclipse before. I should say total solar eclipse is spectacular. Partial solar eclipses are not that interesting. Anyone has seen a total solar eclipse before? No one? Yes, I see someone. And then you know how spectacular that is, right? That when a total solar eclipse happens, the whole region gets really dark, the sky gets dark, and animals will get crazy because they don't know what is happening. All of a sudden, in the middle of the day, the whole sky gets so dark. It's just like night. And so I've seen two solar eclipses, total solar eclipses before. And it's just a very interesting experience that the birds will go crazy. They think it is night again. And then so they're going back to their home, to their nest. And then dogs will bark like crazy because they don't know what is happening. And also that the temperature will cool down in the middle of the day dramatically, and you will actually feel a big chill when the total solar eclipse is happening. So the most recent time I saw it was in 2017, August 21st. I was actually in Kentucky. I was at the University of Kentucky. I was teaching there at that time. And a total solar eclipse happened, and Kentucky was in the right location. And I actually took some pictures of the total solar eclipse during that time with a small telescope, and it was a fantastic experience. And so you see here, these are the sequences of pictures I took that the sun gradually get eaten away by being blocked by the moon. And this is the picture during the total solar eclipse happening, that we are completely blocked, and you can see the corona of the sun, the atmosphere of the sun. And this is time when the sun is going out of when we are going out of the shadow, when the sun starts appearing on the other side of the moon, you see a really bright spot compared to the other part. So this is a tiny portion of the sun just appearing on the side of the moon, and you call this a diamond ring because it looks like a diamond ring, right? It's a ring with a diamond on it. So these are beautiful pictures. Now, some more pictures. My pictures are kind of out of focus because of the temperature change in the telescope. Here is a better picture that is showing that total solar eclipse event. Now I'm going to show you a video. I will show you the total solar eclipse experience. This is made by BBC. You can hear the sound of the video, correct? If there's no sound, then you should let me know. It's 5:28, so that's
sun at the moment. It's obscured by low cloud. The edge of the moon is at this point just beginning to touch the disk of the sun. You can see the sun emerging through the clouds. You can see the disk. Oh, you can see the moon. Can you see the moon on the top? Oh yeah. It's just vanished. You can see the limb of the moon there. Absolutely fantastic. Yeah. You can see the celestial mechanics, the clockwork of the solar system at work. The alignment is absolutely perfect. The sun with other balls of rock. The solar system coming down and grabbing you by the throat.
Okay, so you see that is how dark it can get during a solar eclipse, a total solar eclipse. So if you ever have the opportunity to see a total solar eclipse, you should not miss it. It's going to be a fantastic experience, it's a very strange experience. But in Hong Kong, you have to wait about 800 years to see a total solar eclipse in Hong Kong. The next total solar eclipse in Hong Kong that is visible in Hong Kong is going to be happening the year 2881. We can see some partial solar eclipse in the future in Hong Kong, but those are not as exciting because you don't have the whole sun blocked, and so you don't get the fantastic moment when the whole sky gets dark. And for the one in 2023, on April 20th, 2023, we'll have a partial solar eclipse happening that is visible in Hong Kong. It is going to be a total solar eclipse for Indonesia and for Australia. So this is the region. You can see a tiny thin line here in the middle of the plot. And if you are at those places, you will see a total solar eclipse because that is where the shadow of the moon will pass on Earth. The track of the shadow only goes through this region. From Hong Kong, we can see a merely 3% of the sun being blocked. So it is a partial solar eclipse, and it's a very uninteresting solar eclipse. It's only blocking by 3%. You can barely notice it. And then, but in 2035, the one that is another easily visible total solar eclipse in Asia, that in 2035 will be the one that's going through the northern part of China, actually going through Beijing and Tokyo and many parts in the northern China. This one will be on September 2nd, 2035. And from Hong Kong, we can still just see our partial solar eclipse during that time. It's maybe about 10% of the sun being 10 or 20% of the sun being blocked, still not very interesting. So you really should find out when is the next total solar eclipse. So I recommend that you, in 2035, you want to be at these places, either in the northern part of China or in Tokyo, and then you can see or North Korea, and then you can see the fantastic total solar eclipse. Of course, for other parts of the world, you can see it sooner. For example, in 2024, there will be a total solar eclipse in North America. So you can go to North America in 2024 and see that as well. So there's a lot of people in the world that are chasing total solar eclipse events around the world. So that is very interesting. Okay, so that's about eclipses. So let's take a 5-minute break, and then we can resume to talk about the next chapter of this course. We're going to talk about nature of light and matter. Okay, so now let's take a 5-minute break and come back at 3:38. Thank you. Okay, now let's get back to the lecture. Let me share screen again. So this is the fourth chapter of this course. We are going to talk about nature of light and matter and how they interact. This is going to prepare us for understanding other parts of the lecture. So because the way that we study the universe is not by going there, because the universe is too big for us to travel to the stars directly to study them. We don't know how to do that yet. Interstellar travel is still just only science fictions. It is very difficult to travel to other stars. It's going to take thousands of years with our current technology, and we cannot yet sustain civilization on a spaceship for that long periods of time. And right now, the only thing we can do is to send some probes to other planets, but that is still very expensive and provides very limited information. So we really need a different way of learning about distant objects. And the way we learn about the universe is by looking at the light coming from them. For example, how do we get to know that Venus and Mars' atmosphere are full of carbon dioxide? And we cannot go there, but the way we can get that kind of information is by using light. Light is our primary tool for learning about the universe. By observing the light from the stars and planets, we can learn a lot of information about them. We can measure how fast they're moving. We can measure what kind of temperature they have, what kind of chemical composition they have. That can tell us a huge amount of information just by observing the light from the stars and from the gas in the interstellar medium, from the planets, and that is how we can study them. And light is more than just a messenger, it's also the primary means by which energy is transported throughout the universe. For example, the energy on Earth all comes from the sun, right? It is the sunlight that is powering our whole planet, basically. And almost all the energy on Earth that we are using are deposited by the sun, one way or the other. I mean, we can use solar energy, we can use solar panels to use the solar energy directly. But for example, the fossil fuel energy that we are using, the gas and coal, and those energy, they were actually deposited by the sun long time ago, right? It's through photosynthesis that the sun is depositing its energy in plants. And when these plants die or get eaten by animals, they become fossil fuels. And that is that is the ultimate energy source of on Earth. So first thing we need to understand is what is light. So I'm going to tell you light is two kinds of things. Light is first a type of wave. What is a wave? You are all very familiar with water waves. If you drop a stone in a pond, it will generate outgoing water waves, right? You have ripples on the water surface, and that is what we call waves. In those waves, the molecules in the water, they move up and down. They don't move sideways, but the wave propagates outside. Basically, that energy is being transferred from the inner region, and that is due to the disturbance you created by dropping the stone into the water. And it creates some disturbance in the water, and so that at that place in the pond, that the water is going to move up and down, and that energy gets transported outside and in the form of a wave. So everywhere on the water surface, the molecules are going to start moving up and down, and they transport this motion outward towards the faraway place. And this is what is a wave. This is light wave is very similar to this, and so light wave just behaves in the same way, and it is also doing that. And the one evidence for light waves for light is a wave is that waves should interfere with each other like water waves. So what I mean by interference, or what I mean by waves interfering with each other. So I'm going to show you a movie, a simulation actually, that is recording two pistons that is punching the water surface at regular frequencies. So here you can see two little stones. Just imagine these two little stones. These are electronically controlled. So they're knocking on the water surface. Here is a top-down view of a water surface. So this is, you have water in a tank, and we're looking down at the tank from the top, and you have these two stones knocking on the water surface with regular intervals. Each stone, when it is keep knocking on the water surface, it will generate a constant wave traveling outward that is centered on this stone. And this other stone will also generate waves. You can see these circles, and they're generating these circles. But these two waves, they're going to interfere with each other. By interference, I mean that at any place in the water, they are when the wave passes through them. If that happened to be, if the two waves, the peaks of the two waves are reaching it at the same time, and then at that place, you will have the vibrational motion getting strengthened, it gets stronger. But if you are at a place when that a peak from this wave just happen to meet with the trough or the valley from another wave, then it gets canceled out so that you almost not vibrating at all in those other locations. And that is what we call the interference of waves. And if light can make this, then that will prove light is a wave. So first of all, let me show you this movie. So if you have these two stones knocking on the water surface, each stone will generate an outgoing wave, and the wave will have a round pattern. But these two round circles, they will interfere with each other and generate this pattern. And you can see that if you are looking at this, suppose you are setting a straight line here, and you will see that at these locations, you can see I'm not moving my cursor anymore, so that my cursor is pointing at a fixed location. And you look at this location, when it is dark, that means it is going into a valley. And when it is bright, means it is you're seeing the peak of the wave. And you can see that the waves are passing through the location of my cursor. And that is meaning that at that location my cursor is pointing at, the water in that place is going up and down very strongly. However, if I move my cursor over here, you can see at this location, the color is almost not changing, right? It's always this kind of grayish color. It's not going through black or white. And that is because at these locations, the two waves happen to cancel each other. And so that one wave is in the peak position, the other wave is in the valley position, and they just happen to cancel out each other. And so that at this location, there's almost no vibration in the water. And so you can see in these locations, they all have very strong vibration. So that is when the two waves are adding up to each other, so to increase the vibration. And here as well, this is also a place when they can strengthen the vibration. And this is also a place where they can strengthen the vibration. But in between these groups, these locations, the vibration is get canceled out because the waves happen to cancel out each other. And the same thing can happen to light, that if you have a light source coming out of this little hole on a screen, so if I have put a light bulb right behind here, and it will produce a round traveling wave, and then if I put I put another screen and then drill two slots on the screen, the two slots will become two independent wave sources, or not completely independent, but two wave sources. And these wave sources will have the same characteristic because they come from the same origin. And so they can, just like water waves interfering with each other, they can also interfere with each other. And at these locations, you will have the two waves interfere constructively. That means they will add up, the vibration will add up, and you have really bright light. But at these locations, the waves will cancel out each other, so you have almost no light at those locations. So on this screen, if this is a photographic film, and then you can actually record these interference patterns. So this is how we know the light is a wave. This is because it can have these interference features. We can set up a lab to demonstrate interference of light, so that you want to have two light sources that is correlated, they can interfere with each other, and that proves light is a wave. But light is different from water. There's no molecules in there, right? For waves in water, it is water molecules that are moving up and down. But light travels in a vacuum. Light can travel in a vacuum. It doesn't need any medium to travel, and basically travels in empty space. So what's moving up and down as the wave passes through? When I say light is a wave, what is actually making the vibrational motion? It is the electromagnetic field. It is the electromagnetic field that is actually producing the vibration. But what is the electromagnetic field? So we need to review a little physics, so that in high school or middle school, you probably have heard a little about this. If you have a positive charge, you have a proton, for example, that have a positive charge, or an electron that have a negative charge, they will generate an electric field around them. Just like the gravitational field that the Earth has. Electric field is also a kind of force that can be applied on things that have charges. That means they have positive charge or negative charge. And so that is an electric field. It's not something that is you can touch. It is sort of it's like it's a force field, and you can only feel that force if you have a positive charge or negative charge. But otherwise, if you are a neutral and you're an insulator, you would not feel that electric field. But there is a field that is in existence around anything that have charges. So that is what we call electric field. And also there's magnetic field, which you probably all have played with magnets before when you were kids, or in physics experiment, you probably have played with a magnet. A magnet have a north pole and a south pole, so it has two opposite poles. And when you have a magnet, it can generate a magnetic field. And the magnetic field lines will go from the north pole of the magnet to the south pole of the magnet. And this can also apply a force on anything that have that is magnet, right? Magnetic. Anything that is magnetic can also feel this force. For example, iron. If you have a bunch of iron dust, then you can they will you put them around this magnet, they'll get attracted to either of the two poles, and they will actually form lines that is tracing the magnetic field lines. So this is also a force field. So there's the electric and magnetic fields that is produced by charges and magnets. But actually, even the magnet is actually related with electrons inside the magnet. So what is really producing the electric field and magnetic field are just electrical charges. If you have an electric charge, for example, a proton or an electron that is stationary, if it is staying at rest, meaning it's not moving, then it can generate a stationary electric field. But if you let it move, if you have let the electrons or protons run through a wire, that you generate an electric current, and that will have that is basically a moving charge. Moving charge can produce magnetic field. So in high school, you may have learned that you have an electric current in a wire, and that wire will actually generate magnetic field around it. And so moving charges produce magnetic field. But when will we produce electromagnetic waves is that you have to have a charge that is being accelerated. When you are accelerating a charge, not just simply moving, simply moving at a constant speed, you will have just generated magnetic field. But if you have charge being accelerated, that means the electric field is going to change and the magnetic field is going to change in space. So at any particular point in space, at that position, the electric field is going to vary and the magnetic field is going to vary when the charge is being accelerated. When they vary, the changing electric field will generate a magnetic field, and the changing magnetic field will generate another electric field. And then it starts to form a wave that is called the electromagnetic waves. So this is what James Clerk Maxwell came up with. So that is how the electric field and magnetic field can combine to form electromagnetic waves. So that is what we call light. Light is actually electromagnetic waves. Light waves consist of self-propagating, oscillating electric and magnetic fields that are perpendicular to each other, and they can move in space as well, because that when the electric field is changing, it generates magnetic field, and when the magnetic field is changing, it generates electric field, so that you start to have propagating effects. That these local disturbances start to propagate to far away distances, and so that you have a propagating wave, so that the waves start to travel in space. So in this picture, in this animation, you can see the red wave pattern is telling you the electric field, and the blue wave pattern is telling you the magnetic field. And both the electric field and magnetic field at any location is going to vibrate. You can see the electric field is changing and the magnetic field are changing with it. And as a result, you generate an electromagnetic wave that is propagating in a direction that is perpendicular to the direction of these field directions. And this is what we call we call light, electromagnetic radiation. Excuse me. So this is kind of pretty tough physics. So I'm not, you don't have to fully understand why changing electric field will generate magnetic field or vice versa. But all you need to remember is that light are electromagnetic radiations. And what is light? Light is actually an a changing electromagnetic field, and that is propagating in space. It can propagate in air, it can propagate in water, it can propagate in glass, but it can actually propagate in vacuum. Even if you have nothing, the light can actually propagate because it is an electromagnetic wave. As long as it generates those fields, it can propagate. And so that is the nature of light. it is an electromagnetic wave. That is, we also call light a radiation. This word radiation doesn't mean radioactive stuff, right? This has nothing to do with nuclear bombs or radioactive stuff. This is when we say radiation, we just mean light or something that is a propagating wave. That is what we call a radiation. So electromagnetic waves is light. Okay, and then there are some some properties of waves that you need to remember. And for example, the first thing is wavelengths of light. So here you can see a picture of ocean waves. So when you go to the beach, you can see ocean waves, and you will probably notice that the distance between these waves are roughly constant. And so you have a wave that is traveling towards you, and you can see the next wave coming and then the next wave coming. The distance between these peaks, these wave peaks, is what we call the wavelength of a wave. So the definition is the wavelength is the distance between successive crests or troughs in an electromagnetic wave. So here is a light wave, and we can see here is the crest, or you can also call it peak. And here is the trough, or you can call it valley. And if you measure the distance between two consecutive peaks or two consecutive crests, this is what we call the wavelength. This is the distance between them is the wavelength. And we typically use the Greek symbol lambda, this Greek symbol lambda, to represent the wave, the wavelength. So wavelength is denoted by lambda. Another property of wave is the frequency of it. When the wave is traveling, you can put down a marker at any place in space, and then you just count how many waves pass through you every second. Okay, how many waves pass through this marker every second when the wave is traveling, and you count how many crests you have every second, or how many troughs you have every second. Either way, either the crests or the troughs, but not both at the same time. You just count the number of wave crests that pass a given point in space in 1 second is defined to be the frequency of the wave. That tells you how fast it vibrates, right? And then because of every crest that pass through you at this point, that means this point have gone through one round of vibration. And you have two waves, two crests passing through you every second, then you have two vibrations. You finish two consecutive vibrations. So that is the frequency of the wave. And quite often we denote the frequency by the letter F or the Greek letter nu as the frequency. And it has a unit of hertz. What is this unit of the frequency is hertz. And what does hertz mean? It's just one vibration per second, or two vibration per second. It's so the hertz just means 1 per second. So it is basically inverse of second. So it's the hertz unit is the same as 1 over second. And so if you count two waves passing through, two peaks passing through a particular place every second, then the frequency is 2 hertz. So if it's 2 per second, it's 2 hertz. If 10 per second, it's 10 hertz. And frequency and wavelengths are related to the speed of light. In this way, if you say, okay, I count at this place and count how many waves pass through me every second, that is my frequency, right? So if you count how many waves pass through me every second, so per unit time, so you have set a unit time or either second or minute, as long as it's unit time, and that is the frequency of the wave, and you multiply the number of waves with the wavelength, which is the length per wave, and then you get the total length that is traveled by the wave every second, right, per unit time. So that is wavelength times the number of waves gives you the total length traveled, and that number of waves is counted in a unit time, And so if you divide total length by the unit time, you get a speed, because length divided by time is speed, right? So how much distance you can travel every second, that is the speed. So this is basically the traveling speed of the wave. And in the case of light wave, it is basically the speed of light. And quite often we use the letter C to denote the speed of light. It's a very fast speed, and it's a constant. And you can notice here that this is the wavelength of the wave multiplied by the frequency of the wave, because the number of waves per unit time is basically frequency. That is the definition of frequency, right? So when you multiply wavelength with frequency, you get the speed of light. So remember this, wavelength times frequency equals the traveling speed of the wave, or the speed of light in this case. So lambda times f equals c. And that because wavelength of light, as a speed of light is a constant. Speed of light in vacuum is a constant, right? And then, so the wavelength and frequency then have an inverse relationship. When you have a longer wavelength, you're going to have a lower frequency. Or when you have a shorter wavelength, you're going to have a higher frequency, because the product of these two quantities is a constant. When you multiply lambda with f, you get a constant c, and this c is equal to 3 times 10 to the 8 meters per second, or 300,000 kilometers per second. So that is a constant. And so the relationship between wavelength and frequency is that they're inversely proportional to each other. That when you make the lambda bigger, you have to make the frequency smaller. When you make the lambda smaller, you have to make the frequency larger, so that they multiply to the same number. And this figure illustrates this as well. So all these waves are light waves, and they're all travel using a particular unit. That's 1 multiplied by 1 is 1, right? So that so a longer wavelength, you have less vibrations every second, because that these waves all have to travel at the same distance. If wavelength is longer, you only need to vibrate once to cover this distance in 1 second. But if the wavelength is smaller, so if you say the distance between two consecutive crests is smaller, let's say that the wavelength is half of the bottom one, then you have to vibrate two times in order to cover the same distance in 1 second. So that means that every second you have to have 2 crests going through this parting space. And so this frequency has to be 2 hertz. And if the wavelength is 1/2, then the frequency will be 2 hertz. And if the wavelength is 1/4, then the frequency has to be 4 hertz, because each wave is smaller, so you have to vibrate 4 times in order to cover the same distance, okay, within 1 second. So you have to vibrate 4 times within 1 second in order to cover the same distance in 1 second. So that is the relationship between frequency and wavelengths, and that is something you do need to remember. Long wavelength light has a low frequency, and short wavelength light has a high frequency, okay? Questions? Or if this is hard? Okay, now let's move on. So actually colors, what is colors? Colors are actually just representing different wavelengths of electromagnetic radiations. You probably all have seen rainbows before. Whenever it rains, and if the sun is also happen to be out that from a distance, you will see rainbows in the direction that is opposite from the sun. So in this picture, the sun is shining from behind the photographer, and you can see this beautiful rainbow. This is because the raindrops in the sky those are water droplets. Those water raindrops, they can diffract sunlight into different colors. And these different colors actually represent different wavelengths. They're all electromagnetic radiation. They're all electromagnetic waves. They just happen to have a different wavelength. And that is why our eye will see them as different colors. And this is first proven by Isaac Newton when he was using a prism and diffract the sunlight into different colors. If you light sunlight, which looks white, goes through a prism, you can decompose it into multiple colors, or you can say you can disperse it into multiple colors and form a rainbow pattern. And the rainbow pattern goes from red, orange, yellow, green, blue, indigo, and violet. And it always goes in that sequence because this color sequence is actually a sequence of wavelengths. Red light has the longest wavelength, violet light has the shortest wavelength, and these colors has to be ordered in this way because this is ordered by their wavelengths. So these different colors, what are the true meaning of colors? It's just that they're electromagnetic radiation with different wavelengths. Because the red light have a longer wavelength, and they actually bend. The red light have longer wavelengths than violet light. They bend by different amount by the glass. In vacuum, they all travel at the same speed, but in glass, they start to differ by a tiny bit, and that is what's causing them to get dispersed into a spectrum. And we call this sequence, this order of light, a spectrum. When these different color light gets dispersed into a color sequence, we call it a spectrum. And so you should remember this color sequence, and you can remember either in Chinese or in English, and you want to do it in English, this is a good way to remember it. So people make up these mnemonic, trying to help us memorize things. So this, you can see the initials start with ROYGBIV. And so you can make up a name that is called Roy G. Biv. And so that is red, orange, yellow, green, blue, indigo, and violet. So this is the sequence of colors that represent electromagnetic waves going from long wavelengths to short wavelengths. Okay, so that's long wavelengths, short wavelengths. Okay, that's the wave nature of light. I think I probably should end the topic here, and then we'll continue with this topic in next lecture. So next time I will tell you light is not only a wave, but also a particle. And light actually have a very strange feature. It's not just a wave, it's also behave like particles, like a bullet sometimes. Okay, so now that's the end of today's lecture. Thank you very much for joining. Have a good day.
Thank you. Bye-bye.
Thank you. I will upload the slides to Blackboard so you can see.
Okay.
Thank you.